Hello everyone, and welcome to the NEATEC Electronics Series. This episode is about Common Emitter Amplifier DC analysis. So let's get started. Alright everybody, so let's start talking about DC analysis for the Common Emitter Amplifier. So the first thing let's do is let's simply draw a common emitter amplifier, right? So what do we have on top? We have VCC, right? Come through a resistor. This, by the way, is RC. Then we're going through the bipolar junction transistor. Down here, we're going to draw another resistor. This is RE, and then we're going to ground, right? Remember, this is your base. Again, this is your collector, and this is your emitter. Now if we come down here, we have to bias your base, don't we? So we're going to draw a voltage divider. There it is. Now this one you can simply call, these resistors you can call R1 and R2. Alright? Now if you remember, this is your output and this is your input, right? So we have a capacitor here, comes down to your AC component right here. This is your input. Just put it in here. In your output, you're going to go through an output capacitor. It's going to come over here, come down. It's going to draw a resistor there. This is your load resistor right here. So your load resistor is going to come down here and go to ground. And this is R sub L. And finally, let's do something. I drew R sub E here. Let's move it so it's over here, alright? Because what do we have to put here? We have to put our bypass capacitor right there, right? That is your common emitter amplifier right there. This is C1. This is C2, this is C3. I'm not sure if the numbers correspond to what they were before, but this is, I'm going to call it, instead of C1, this is just Cn. This here I'm going to just name C out, and this is going to C bypass. I'll call it BP, like the oil company, right? So, there you have it. Now, what are the two rules? What is some of the one rule, I'm sorry, for the DC analysis? So let's circle it. Capacitors act as opens for DC analysis. Okay, so if I say they act as an open, basically this is like it's been cut, the wire cutter, right? This one here, it's been cut. right? It's like it's not even there. I took part of the R off there, didn't I? I gotta watch myself. Look at this capacitor. It's like it's not even there, right? Because they act as opens. I'm sorry, yes, as opens, right? So if we redraw this thing, all it is, I'm just going to draw a little arrow here, just to redraw it for you. That's simply going to be VCC from here to your resistor. RC, RE is your base, right up here. Let's connect them here. Boom, boom. R1, R2. This is important, because now you're going to use this model right here. This is what you're going to use to do your DC analysis for this amplifier, right? You might be given this right over here. You might be given that, although these would be, the capacitors would be in place and everything, but you just got to understand that for DC analysis, this is what it looks like. AC analysis, it's going to look like something different. Okay? So that's the first thing I want you to understand, is capacitors act as opens for DC analysis, because DC voltage will not go through it. And when you, or current will not either. And look at it. It's two plates that are apart. They aren't touching. Kind of the illustration of it gives that away. Alright. I'm going to clean this up, and I'm going to come back shortly. And I'm going to redraw the amplifier for you, and we're going to go through two types of analysis. Okay? Alright, everybody. So welcome back here. And as you can see, I simply rearranged some things here. One thing I want to bring to your attention is I had a spelling mistake over here. As you can see, I changed that to the word as. So capacitors act as opens for DC analysis. That was my mistake. So I copied the circuit we have, and I just put it over here to the left. So let's try a DC analysis, just a very basic DC analysis that you might use in lab. And there's two ways to do it. One is using Thevenin's theorem, and there's another way that's like a shortcut. Okay, so we're going to do the shortcut first, and then we're going to do Thevenin second, and I'm going to show you the difference. Okay, so generally what you want to find out first is you want to find out VB, and this is generally, this isn't always the case, this is how I do it. Alright, so VB, what does VB equal? Voltage of your base. Well, that's between R1 and R2. You see that over here? So that's basically going to be a voltage divider, and it's going to be R2 divided by R1 plus R2 times VCC. That makes sense, right? And that gives you your voltage right here at your base. Now, once you know your voltage at your base, and remember, this is your emitter, and this is your collector. That's your base, right? So, remember, the voltage drop between your base and emitter, that's termed VBE. That is a constant, and that depends on the transistor you're using. But we're going to assume silicon, and we're going to assume that it's 0.7 volts. Okay? Now, so whatever VB is, then you know VBE, you're going to have another 0.7 drop. So VE, which is the voltage right here at your emitter, will be right there. That's your, what we're talking about. VE is going to equal to your base voltage minus VBE, which really that's just equal to VB minus 0.7 volts. That's what that is. So now you have VE. So if you know your voltage down here and you know what RE is, well, you can calculate what? Your current, your emitter current. So that's going to be voltage at your emitter divided by RE. That gives you your emitter current. Now once you know your emitter current, then this leads into your collector current, because your collector current is approximately equal to IE. Isn't this beautiful? And if you know your collector current, VC is going to equal VCC minus IC RC. And if you look at it, you can see that, that's no pun intended, you're going to have a voltage drop right there. So you're starting with VCC, you know the current and you know the resistance, so you need to subtract the voltage drop across RC to get VC, right? And finally, VCE is going to equal VC minus VE. And here's your VE, which you already figured out, and here's your VC. And that is your DC analysis. Let me qualify that. That's one way of doing your DC analysis. Now you may see it written in another form, done differently, and you might get slightly different answers. And let me show you where that comes from. This was the shortcut method, all right? So this, what I just showed you, was I termed as the shortcut earlier. Now if you're going to use the Thevenin approach, we're going to have to do something. If you have a base voltage, a base, this is your base, right? It's coming in here to your emitter. Here's your collector. That's your collector, right? Now remember, you have a resistor there on top and a resistor below, right? And this went up to VCC as well. It was tied in here, and we just went up here to VCC, right? It's getting kind of crowded up there. I apologize for that. Let me just see if I can bring this down for you to make it a little clearer. Okay? Let me just erase that here for you. Sometimes when you get talking about something, you don't pay much attention to what you're drawing. It's more attention to what you're saying, right? Now this we're going to say is VCC. All right? It's just connected here, and that's how we did it. So now suppose we rewrote this, and I'm just going to bring this over like this. Suppose we had the collector going to VCC, a VCC source, right? And then suppose we had this one right here going to a separate VCC source, right? I'm just going to draw it right up on top here. It's just a separate VCC source. VCC. Okay? Now, you can see that this R2, this goes to ground, right? And here's VCC. Okay? So let's Thevenize this right here. Let me draw Let's just Thevenize that, all right? So we want to get the voltage at that point, right? So V Thevenin what's that going to equal? We just want the voltage at that point. Well, we know what that is. It's what the other one was. It's going to be R2 divided by R1 plus R2 times VCC. All right? Because we're basically looking right here, right? Now, the other thing we have to do is RTH. And remember, when you do RTH, you replace your source with its internal resistance, and we're going to assume that the internal resistance is basically 0, okay? So when you do that, if you want to redraw these things, right? If the base is coming out, have it right? If your base is coming out here, right, this is what we're doing, right? Suppose this was where your base was. You have one resistor, R2, coming to ground, right? R2. And we have another one, which is R1. And this is going to your VCC, but remember, we replaced it with a short. And that's going to ground, right? So basically you have two resistors in parallel, R1 and R2, right? So that is going to be rewritten as R1, R2 divided by R1 plus R2. Now if you have questions about this, I advise you to go back to the Thevenin video and take a look at it. But this is an important concept, because what that leads to, right, if we're going to just redraw this thing, the whole thing, you're going to have a source, which is, say, let's just call it V Thevenin right here. You're going to go through a resistor, and that's going to be R Thevenin, right? And that's going to go to your, I'm going to attach it right here, it's going to go to your base. Your base will come down like this. It'll come down your emitter to your emitter resistor, and then the ground. And this would go up through your collector resistor to VCC, right? Now, at this point, this is where it gets rather interesting. Let's start here. So if we're starting at V Thevenin, let's go through this. Let's go through it this way, shall we? We're going to go through it this way. Down to ground, right? That's what we're interested in here. So let's look at this. You're going to start off with V Thevenin. We're just using Kirchhoff's law, which basically states that if you're starting at a voltage, all these voltage drops have to sum up to this voltage, which means it's 0, right? So the sum of all your voltages has to equal 0. That's what Kirchhoff's law is. So we have V Thevenin. We're going to subtract the voltage across your Thevenin resistor. So I'm going to call that VRTH, right, the Thevenin resistor, minus VBE. That's your base. Here's your emitter. So we're looking at this voltage drop right here. And then minus VRE, which is, there's your RE right here. That's RE. And this here is your RC, right? Minus RE equals 0. All right? So let me write this a little bit neater over here. Okay, so what we just said now, I'm gonna write it nicely underneath here. Just the same thing. V Thevenin minus V, voltage across your Thevenin resistance, minus your base emitter, voltage drop, minus your voltage across RE equals 0. Now let's put Thevenin on the left side of the equal sign, right? So we're going to say V Thevenin is going to equal VR, your Thevenin resistance, voltage drop across your Thevenin resistance, plus VBE plus VRE, right? Now, here are some substitutions that are rather useful at this point. And I gotta see where I'm gonna fit all this stuff, aren't I? Let me move this. I hate it when this happens. You just want more space, but unfortunately there's just so much. I'm moving it over here, alright? Let's move it right there. And we'll move this one over just a tad here. Okay. Now, guess I messed that up there, huh? Oh well. We'll just leave it for now. Let's keep going, all right? So I'm gonna draw this again. VTH is gonna equal, now VRTH, that's the voltage drop across your Thevenin resistance. That's going to be the same as your base current, right, times what? RTH. Remember your Thevenin resistance. Remember V equals IR, right? Always go back to Ohm's law. It seems like that's where everything always leads, right? Now we're going to say plus VBE. That's a constant. We know what that is. Now here's another thing. VRE. That's going to be equal to what? IE RE, right? Remember, V equals IR, your emitter current times that resistor, emitter resistance, is going to give you what VRE is, right? Your voltage drop. Now, I'm going to rewrite this. Remember, your IE, there's a relationship here I want you to remember. We want to replace this base current with IE. So what is, remember this, if you have IB times beta, that's going to equal IC, right? Which is approximately equal to IE. Got it? So if we're going to say that, we can say, therefore, we can say IB, we're going to say is approximately equal to IE divided by beta. Okay? That's a key thing to remember. Now, at this point, I'm going to have to get some more space, so I'm going to have to say goodbye to our other way of doing it. I kept it there as long as I could, but I just couldn't keep it there anymore. Let's get rid of this one here. Let's just take care of you guys too. How's that? I'll just do this one right here. Now, let's take you up here, guys. Now, what I'm going to do just move you guys over here. Just keep it, just so you guys can have this to take notes from if you want to take further notes on this, okay? And we'll just move the V Thevenin right where it was. V Thevenin minus around there. Alright? Now, we'll move you up here. So if we look at this, we have this is wonderful, right? So now we have a replacement for that. And if you take a step back and look at proofs, a lot of times that's what you're trying to do. You're trying to get your variables in term that you don't know in terms of items or variables that you do know, right? So let's rewrite this now, right? So we're going to say VTH is going to equal, what do we say IB was? That's going to equal IE divided by beta, right? I'm going to put that in parentheses for you, times RTH, right? Plus VBE plus IE RE. Now, let's do something else. These two terms both have IE in them, right? When I say these two terms, I'm talking about this term right here and this term right here. So let's rewrite this again. And what we're going to do is say that this is equal, I'm going to bring this term over here, IE times, now if I look at this one, it's going to be RE plus RTH divided by beta, right? Plus VBE. You see that now? That's VTH. And that's an E here. I don't know if that's very clear. IE is equal to RE plus R Thevenin divided by beta plus VBE. That's just basic algebra, right? So I want to get this, now I want to get this value here in terms of IE, right? So if we do that, it's pretty straightforward. We're going to subtract VBE from both sides, and we're going to end up with this. IE is going to equal VTH minus VBE divided by RE plus RTH, R Thevenin, over beta, right? There should be a little tail there. There's a little tail there, right? So if you notice, when you look at this, come over here and look at this right here. We started out here, right? We started out with our VB, right? Then we then had to subtract the voltage here. And if we know what VE is at this time, right? This was our other way, our shortcut. And how did we get IE? We just took VE and we divided it by RE, right? How did we get VE? We took the base, we subtracted VBE, and we got it. If you notice, it's very similar. The only difference is this term right here. That's the difference, RTH over beta. So this is what the discussion is, or the logic behind it, is generally RTH, your Thevenin resistance, divided by beta, which is usually 100 to 200 or more, depending what your resistor is. That's considered very small and almost insignificant. So many times that's ignored. And that's why you don't see it. But there's two ways to calculate it. Just be aware that if that is necessary, I mean, if it's not insignificant, you need to include it, okay? So that is a discussion. That's the second way of doing it. So once you know IE, all right, I'm going to write this formula down now over here. I'm going to take this off. I'm going to take this off here. Okay, I'm going to take this off here. Now, what I'm going to do, I'm going to move this one. We know what IE is, right? So let's just go through this now. If we know what IE is, we're in really good shape, okay? So once we know what IE is, then we can say, okay, if we know what IE is, what's IE approximately equal to? Give you a hint, it's right here. It's your collector, right? We know IC is approximately equal to IE, right? So you know what IC is, right? Now look, if you know what RE is and you know what IE is, you know also VE, right? VE is going to equal to IE times RE. Right? Here's your RE. If you know what your emitter current is, you can calculate what your voltage is there, right? Very useful. Now, if you want to figure out your base voltage, you would simply take VB is going to equal to your emitter voltage, VE, plus 0.7 volts. Remember, your Thevenin voltage is without any load on it. So when you apply a load, your voltage that you're looking for may change. That's why you have to add the 0.7 here, right? Then once we know what that is, we know VC, this is all the same actually, is going to be equal to VCC minus ICRC, and you know what those values are, right? And VCE is going to equal VC minus VE. And you know what those are. Here's your VC and here's your VE. Alright, so there's two ways to do it. So at this point, I'm going to have a problem here. And we're going to go through an example, and we're actually going to calculate it, and we're going to see how it works. All right, folks, see you in a moment. All right, everybody, let's do a problem. And I wrote a circuit right here, and I included the capacitors for both the output, which is right here, and the input, right? So remember, when you write the circuit, basically the capacitors act as an open, like it's been cut, right? So basically this line here we can get rid of, and this input here over here we can get rid of, right? So let's take a look at it. So here we are. So let's try this now. Let's figure out what VB is, right? VB is going to equal, what is it going to equal? It's going to equal 4.7 kiloohms divided by 22 K kiloohms plus 4.7 kiloohms. All right. And this whole thing is going to be multiplied by 15 volts, because that's your VCC, right? And then this whole thing is going to be equal to 2.64 volts. By the way, we're doing the shortcut method here, right? So we know what VB is. Now, what's the next thing? What is VE equal to? VE is going to be equal to VB minus VBE, which is going to be equal to 2.64 volts minus 0.7 volts is going to be equal to 1.94 volts. Get it? Now, if we know VE right here, I'm just going to point to it. That's where VE is, your voltage at your emitter. And we know this resistor here, which we do. We can determine the current, IE. That's very important. This gives you a lot of information. So IE is going to be VE divided by RE. Got it? Which is going to be equal to 1.94 volts divided by 1K, I could put 1.0K, which is going to equal 1.94 milliamps. Now, if we know IE, what else do we know? IC, because IC is approximately equal to IE, which is equal to 1.94 milliamps, right? And finally, if we know IC, we can calculate VC. And that's going to be equal to VCC minus ICRC, which is going to be equal to 15 volts minus 1.94 milliamps times, and what's that equal to? It's equal to 2.2K, right? Times 2.2 kiloohms, right? And that's going to equal, I think that's 11.6 volts, right? And then finally, we can do VCE, can't we? That's going to equal to VC minus VE, which is going to equal what? Well, it's going to equal to 11.6 minus 1.94, which is going to equal, what's that going to equal? Let's get out the old calculator. I forgot to do this one. All right, this will be interesting. Well, why not? Let's just there it is. Let's do it. You guys can see it right there, right? This is beautiful, right? 11.6 minus 1.94, and what's that going to equal? 9.66, right? So this is going to be equal to 9.66 volts. Beautiful, right? Now this is generally how you're going to be doing it in the lab, right? Unless someone asks you specifically to do it the method we did with Thevenin, where you take beta, but you utilize beta. But in this case, I didn't give you beta, so if you're not given beta, you're going to have to do it this way, all right? Now, another thing is, if you've looked at resistors, a lot of times beta can be quite variable, all right? You might be given a range. If you look at the spec sheet, it will give you a range of beta. So you can use Thevenin to determine if that's going to affect your circuit or not. Generally, this is the way you would do it, all right? All right, everybody, I hope this last problem helped you. And remember, when you do these problems, take your time, watch your units very carefully. Remember, we talked about this earlier. There it is. So remember, if we're talking milli, That's a small m. That means milli. And that's equal to 1/1000th. Alright? So, if you notice, we have 1.94 milliamps. That's going to be 0.00194 amps. Because remember, this is 1/1000th here, right? Tenths, hundredths, thousandths, right there. So there you go. Alright? Remember kilo, K, if you're talking kilo ohms, that's equal kilo, which is equal to 1000. So if we have 22K ohms, that basically is equal to 22,000 ohms. Alright? So just remember that. Learn how your calculator operates and do these exercises and make sure you come up with the same answer as I've had here. Also talk to your friends when they're doing it as well, because that may help you as well. You know, understanding how they use their calculator may help you understand how to use yours. Alright folks, thank you for watching. Bye now.